Ruobing Don.
Yes.
Today from Princeton. Ruobing works with John and Numerical. He's a fourth-year graduate student. He works on both theory and observational sides of the high physics. And today is special because today is his birthday. So, welcome.
So thank you. So it's a real pleasure to be here. Thanks for having me. So, so I think I introduced. I'm a first-year graduate student from Princeton. So the topic, as the title suggested, is protoplanetary. I talk about both theory and observation. So I work with Numerical, Tombstone, John and June, some friends from Princeton, Lee Herman from Michigan, Robert from Madison, and John Hashimoto from Japan, and various other seas collaboration. So just one slide for the advertisement. So except protoplanetary disk, I have also been an interesting in this subjects like bubbles and galactic clusters, planet debris around white dwarf instead of kinematics in Milky Way. My office is 1413, so if anyone interested, please come to talk. So, all right, so a brief history of, or like a short version of the story, planet and star formation. So everything starts from a molecular cloud. So the molecular cloud collapsed to form protostars. So initially, the stars is surrounded by a dense envelope, and their disk and maybe jets in it. And as time goes on, first the envelope dissipates, so leaves you a gaseous protoplanetary disk. Then, after some time, the gas in the disk also dissipates, leaves you a debris disk. Then, after millions of years of evolution, the planetary system reached a final dynamic stable configuration. This is the planetary system we see today. So this is well, this is a little out of date. So this is the number of planets detected as a function of time. This is up to 2011. So now we know Kepler already essentially shipped the vertical axis. But the point is, so it's essentially almost all the planets here are discovered at this stage. So what I'll be talking here today is what happened here at the protoplanetary disk. So the gas is still here, and the planets are forming a lot of stars going on here. So the investigation here can be carried out in both the theoretical way and an observational way. So theory, on the theory side, people study theoretical planet formation, disk planet interaction, gap opening, planet migration, etc., etc. So observationally, people are trying to detect the signposts of planet formation in disks. So as you know, it's very hard these days to people are looking at the pre-transitional and transitional disks, which are believed to have some relation with planet formation. So here's my outline. So I'll talk about both theory and observation. So on the theory side, I'll talk about some of my work with Tombstone and Norman on numerical simulation of this planet interaction. And on the observational side, I'll talk about the SEAS project, which is a direct imaging project using the Subaru in some of our discovery to tell like a different version of the pre-transitional disk. So I'll start with theory. So what is this planet interaction? This planet interaction happens when the gas in the disk is still around and the planet just formed, and the planet is going to dynamically interact with the disk through gravity and excite density waves. So the inner part of the wave and planet is going to exchange angular momentum. The inner part of the disk is going to push the planet outward, and outer part of the planet is going to disk is going to push the planet inward. And the difference between the torques on two sides will determine the planet migration rate. And if the perturbation is strong enough, you can also maybe open gaps. So the basic thing in the planet-disk interaction field is the density wave. So the excitation and propagation of density wave can be divided into two stages: the linear stage and nonlinear stage. The theory in the linear stage is developed by Godunov and Tremay more than 3 decades ago. So essentially, if you decompose the potential of the planet into a series of Fourier harmonics, then you write down the dispersion relation of the disk, then the singularity of dispersion relation will give you resonances in the disk, particularly the Numerical resonance. So the planet excites a density wave on its orbit. Then the density wave propagates away from the planet. On its way out, it's going to encounter a series of invariant resonance from large M to small m. And analytically, you can calculate the torque exchanged by the disk and the planet at each invariant resonance. And if you sum them up, on one side you get the total torque on one side. Then if you differentiate the two sides torque, you get the net torque, which would directly translate into the migration rate. So the propagation of the density wave is in a nonlinear manner, in the sense that the different part of the wave will have a different propagation speed. The high density part of the wave will go at a slightly higher speed. As a result, the profile of the wave will steepen over time, and eventually, when the peak catches up, the wave is going to shock. And after the shock happens, the wave is going to dampen, and the angular momentum carried by the wave is going to be dumped into the disk to drive the disk evolution, such as gap formation. So in a nonlinear state, the theory was worked out by Jeremy Goodman and Numerical. The two key questions we try to answer is where the shock happens in the wave and how the angular momentum gets dumped after the shock formation. So in the past 2 decades or so, numerous numerical work has been done to study this planet interaction. And people all compare the numerical result with analytical prediction. However, the vast majority of them compare these 2 quantities, the planet migration rate and the gap opening mass limit, with theory. Those quantities are actually only secondary quantities. They're derived from the primary quantities, which are the fundamental quantities, like first step, which you get in the theory, are the primary quantities here, include density profile, density, the torque exchange between the 2 at each harmonics, where the shock happened, and how the angular momentum decay after the shock. So, for example, the torque exchanged by the disk and the planet at each invariant resonance is the first step. Once you get this, you sum over all the invariant resonance, you get torque on one side, second step. Then you differentiate the 2. The difference between the inner and outer part to do the net torque. This is the third step. This one tells you the planet migration rate, but this is a very derived quantity, high-level quantity. So you run simulation, you compare with theory. You may or may not agree on this quantity, but in either case, it doesn't tell you whether the simulation is correct or not, because you can screw up this part, but you get a correct answer on this secondary quantities. So I'll talk about our numerical works here. So a bit of the motivation. So why we do this work? So the first point is to check the theory. So the linear part has been studied extensively in the past. What we're trying to do is, as I was talking, we focus on the primary quantities. We compare quantities such as the torque at each invariant resonance, the torque density in the physical space, this kind of quantity. One thing we accidentally found in this process is so-called negative torque density, which I'll talk about later. In the nonlinear part, so the nonlinear theory has not been treated seriously before, so not too many numerical works targeting this part. So we essentially quantitatively checked the entire theory for the first time. And of course, just to check the theory is not a super exciting thing, because the theory is, in any case, probably right. There's no need to verify it. Instead, we actually try to ask such a question like this. What kind of simulation gives you correct result? Or what kind of numerical parameters you have to choose? What kind of numerical condition you have to satisfy to ensure your simulation to have good agreement with theory? And so the way we carry out the whole business, we think it could be serve as the standard framework for future forecast. So this is our numerical setup. So we use previous code Athena, which is Godunov code studying gas dynamics. So our simulation is 2D shearing box. So basically a little patch is here. And the initial condition is a uniform fluid. We use this setup because both the Godunov theory and Goodman-Ruffikoff theory are done in this configuration. The planet mass in our simulation is very small compared with previous simulation. We use a lunar mass to Earth mass. Planet. We use such a small mass because we're trying to separate the nonlinear stage and linear stage. If you just stick a Jupiter mass planet into this, then the wave immediately gets shocked and become nonlinear. Then there's no way you can study the density wave in the linear state. So the main numerical difference in our simulation compared with previous work is we use essentially ridiculously high resolution. We use 256 point per scale height. Compared with, I think the highest previous simulation are done with 32 grid point per scale height. So we're almost 1 order of magnitude higher in resolution. And it turns out you have to go with such high resolution to have a very good agreement with theory. The numerical viscosity, well, because we use such a high resolution, the numerical viscosity is very low, which is also needed if you want to study the density wave. The simulation box size is 10 to 20 on one side and maybe 100 scale height on the other. So x direction here is radial direction, y is exponential. So this map is a density map. So the initial density is 1, which is green here. So just a simple example to show how the simulation looks like. So once you put in the planet, it's going to excite density wave and propagates away. There is an initial transient phase. We'll wait long enough until this phase passes away, then we start to measure the properties of the waves. So numerical results. First, we'll look at the linear wave. So this figure here shows you the torque density in Fourier space. In other words, this is a torque at each Lagrange resonance. So the dashed line here is theory, and there is colored curves or the numerical results. The torque exchange between the disk and the planet at each Lagrange resonance is arguably the most fundamental quantities in the entire disk-planet interaction theory. However, after 30 years the theory has been invented, this quantity has never been qualitatively checked. So you see the good agreement here. The deviation here is just because our simulation box is not large enough to catch up the power in the low M's harmonics. And this is the torque density in physical space. So this is torque density as a function of x, essentially, or radius. So this is how much torque you pick up at various positions. So red curve is theory, black curve is numerical simulation. There's no noticeable difference between the two. This figure basically tells you most of the torque is picked up within 1 or 2 scale height from the disk, from the planet. Oh yes. It's a linear circuit. So one thing we did find, which we did not expect, is a negative torque density. So this is a previous torque density in physical space as a function of radius. If you blow out this region, you find the torque density is actually not always positive. It hits 0 and becomes negative after a few scale height. Of course, this is not overall. This is not. This does not affect the final result too much because the integration, the area below this negative part is very small. So the total torque is not verified too much by this phenomenon. But this negative torque here was not predicted in the original version of the Godunov theory. So after we found this in the simulation, so Roman picked up another grad student, Christopher Petrovich. So they actually looked into the series to see whether this thing is real. This does not affect normalization or relevancy, but it is important for us because we want to know whether our simulation is close to absolutely correct, whether this negative thing here is real or not tells you something about the numerics in the simulation. So what they found is actually indeed. So there is some simplification in original form of the dense wave theory. After you make some revision, you actually, the vector is a new theory they derive. The theory also hits zero at the same position with the simulation, and it goes on afterwards. So this thing has actually been called on spot before, such as the Angela and Lulu simulation a few years ago. So if you go out their region here, you also see their density, torque density is zero and become active. However, previously, those simulations are not done in such a way that they're good enough to be quantitatively compared with series. So my guess would be previous authors would just simply think this is some numerical issue here, which doesn't deserve a serious explanation. So moving on to talk about the nonlinear wave. So yes, so in the Godunov theory, so this is a planet, like for example, when the waves hit one of the luminary resonance, in the Godunov theory, the wave picks up the total torque in a star function manner. But what happened in reality is it picked up the wave in this way. So it's a wavy behavior, and the torque for each luminary resonance only approach its asymptotic value at large distance. So if you add all these torques together at this distance, it just happens, some of the negative part gets together, which gives you a negative torque density. So the nonlinear part of the theory, so just to remind you, the two fundamental issues in the nonlinear part is where the wave will shock and how the angular momentum from the density wave is transferred to the disk. So we use a quantity called potential verticity to pin down the shock. Potential verticity is defined in this way is such a quantity which is conserved everywhere in our simulation except when you cross a shock. So this is a potential verticity map. So green is zero. So the fluid comes in this way and this way. The planet here. So this is only half. This is only half of the simulation domain. So this is a density wave here. The wave will shock at a finite distance depending on its mass. So if the fluid hits the spiral wave before the shock happens, nothing will change, and the potential verticity is conserved. If it hits the wave after the shock happens, then you will see a jump in the potential verticity. And after the fluid passes the wave, there's no more shock in front of it. Then conserves this increased value into its deep spot. So this is the map at one planet mass. If you look at the we call it shocking length. If you look at shocking length as a function of planet mass, you get a figure like this. So the straight line here is the analytical prediction in a Goodman and Ruobing paper, and the black balls are simulation done. It's a very nice agreement, except as a large n where the planet becomes too massive that the linear and nonlinear stage cannot be divided clearly, and the theory becomes not correct. So one thing to note here is, the horizontal axis, the planet mass in our simulation is very small. Earth's mass or sub-Earth's mass. However, as the disk is invasive, even this kind of small mass planet can still introduce shock in the disk. Therefore, the density wave can still manage to transfer angular momentum to the local disk, so to open a gap. To show you this effect, I'm showing a movie here. So this is an Earth mass planet. So this is a work Dr. Zhu and Princeton putting together from others. So this is the Earth mass planet we put it in a simulation, and this is density map. So the two dashed red line here tells you theoretically where the wave will shock. So if you run the simulation, you see once the wave shock, there's two narrow gaps open exactly at where the theoretical prediction is. And then as time goes on, the gap gets deeper, and they all also get wider.
How low viscosity?
Oh, you need very low viscosity, right? On one hand, Athena is very good at having a very low numerical viscosity. The other hand, those kind of simulations run with ridiculously high levels, so the numerical viscosity is also low.
And there's no viscosity driven by hand?
Yeah, there's no explicit viscosity. But in any case, so this is to show you in an invasive disk, very small mass planet can still open a gap. Whether it's relevant to real disk or not is another question, but theoretically this is useful. Anything other question?
Yeah, also this is a 2D simulation, which means not integrating any behavior in large height. And the field radius of the planet is very small compared to this scale height.
That's true.
So that means the gravity field up there is actually very different from the gravity of the different.
Yes.
So
the
I don't know if this is going to really happen for the big 2D disk.
So if we start talking about realistic effect, then you can also say there's no magnetic field here, there's no MRI.
No, just a pure hydro-laminar disk. But this is that high, which is not even pure disk. What will happen to the disk?
I think the density wave, the excitation and propagation of density wave in the 3D case, if my collection is correct, you're trying to argue there's one single mode which is in the 3D is very similar to the 2D case. So I guess the wave in 3D can also shock and damps the angular momentum to the local part of this and opens and drives the density material to migrate in that area. And whether that effect can propagate throughout the disk vertically, I don't really know. But those people are running 3D simulation as well. Well, in the 3D case, you directly plug in the magnetic field, so they're mostly interested in the MRI effect. So that's right. So, yeah, so hopefully by now I have convinced you our simulation were correct in the sense it produced excellent agreement with theory. Based on this, now we're at a good point to talk about numerical effects. Essentially, you want to ask the question, okay, now you have good agreement with theory, but this is under what numerical condition? And what if you change some of the condition? How this change is going to affect your result? And to what extent you start to deviate from the theoretical prediction? So eventually, the question to ask is, how do you know whether a simulation is correct? How do you make a correct simulation? Again, the details could be found in our two publications last year. Here I just show you one example which we compare two simulations. One simulation we use a second order solver resolution, which is highest in previous value, 32 degree point per scale height. We use a second order planetary potential with a large softening. This is to be compared with another simulation which is third order solver, higher resolution 256, 3 point per H, first order potential, and a small softening. So the combined effect of potential and softening is in such a way that the planetary potential here converges to the point mass Gm over R potential much faster than this potential up here. So I'm going to show you in the next slides what the effects are, but the final conclusion is this simulation, which is a weaker set of parameters, produces very inaccurate numerical result. So this is the result. I show you two quantities here. First is the density profile or the width profile, essentially the density as a function of y at a, in this case it's x, which is 2 scale height. So basically this is a density cut here. So in both figures, solid lines are our standard simulation. The dashed lines are simulation use typical previous parameter, and the dotted lines are a series. So as you can see, while our simulation is pretty good, if you choose typical parameters in the literature, then your density, the peak of the density wave would be typically 15 to 20% lower than what the theory would tell. This is, of course, people would argue this is not such a big deal. The peak of the density wave is probably never going to be observed in the real disk. Okay, but then let's look at the other panel here. This is showing you the angular momentum flux carried by the wave. So when a wave moves away from the planet, as I was talking before, it collects angular momentum at each invariant resonance location. And if there's no shock, then once the wave collects this angular momentum, it will carry out this angular momentum with it. And so the angular momentum flux increase with radius and reach asymptotic finite value, because here you already finished most of your torque fraction process. And it will only damp once your wave shocks. And once your wave shocks, your angular momentum flux will be transferred from the wave to the local disk. So first thing to look at is the final value here. While our numerical simulation includes theory, you see this is we call literature simulation. This is, you see a 20 to 29% decrease here. This thing here is the total torque on one side. And the difference between the torque on two sides will give you migration rate. If you screw up the torque on one side by 25%, you don't know whether you screw up the same amount on the other side. And there's no way you can tell whether the difference between the two is still correct. This is one thing. The other thing is where the wave shocks. So for this planet mass, the analytical prediction is the wave will shock at 5 and the angular momentum will start to decrease after 5 spiral line. So this is what we see in the Yarrow simulation. The angular momentum flux started to decrease after 5 spiral line. But in the literature simulation, it started to decrease roughly around 3 or 3.5. Where the wave shocks and how the angular momentum is dumped into the local disk is intimately related to the gap opening process. So the final conclusion is, if your numerical simulation, the parameters in the simulation are not good enough, particularly the resolution, which relates to the numerical viscosity count. If you don't reach a threshold, your simulation will have an inaccurate result. We're testing the parameter result here. Whether this effect, to what extent it will be transferred into your migration rate and gap opening mass, is still has not been carried out, but this is a very serious issue for numerical simulation here. So to sum up, the numerical part. So we're verifying the nonlinear and linear density wave theory by checking the parameters, by checking all the primary parameters. The highlights are the torque at each invariant resonance, and where the wave will shock and how the wave will be damped, which I didn't mention here. So, and we also accidentally find the negative torque, which was explained by later revised theory. And the whole process we carry out in this exercise tells you something about numerical parameters. So essentially, high order numerical solver and very high resolution, very accurate planet potential, and small software is needed to ensure an accurate simulation result. All right, so I finished the theory part of my work, so I'm moving on to the observational part. So observationally, I am working in the CITA collaboration, which I'll show in the I guess you can show here. So the CITA is strategic exploration of exoplanet and disks. So it's carried out mainly by 3 institutes, the NAOJ in Japan, Max Planck in Germany, and Princeton. So this project uses 120 nights over a period of 5 years on Subaru. The project do high contrast imaging. So basically to take direct image of the planet and disk. It had 2-part planet and disk. On planet side, directly imaging the nearby stars, hope to find well, of course, to define the planet and to tell you some statistics of planet. On the disk side, it takes polarized image of protoplanetary disk and try to explore the diversity of the disk and the connection between the disk and the planet. So, okay, so what is CITA doing in the disk side? It takes polarized near-infrared image at JHK band. JHK band are 1 micron, 2 micron. So the disk is too cold to give you thermal emission at this short wavelength. Well, except at the very, very inner part. So the other part of the disk, you see those are examples here. You see the near-infrared light. It's because the starlight is scattered by dust in the disk. So the dust in the protoplanetary disk starts with pristine small dust. By small, we mean micron or submicron dust. Here, interstellar medium dust. They will grow and coagulate into bigger size. Various models will tell you once they grow to bigger size, they try to settle to the disk midplane, so that the disk upper layer will always only have the smallest. So the scattering will happen at a scanning surface, which roughly can be characterized by the optical depth at those wavelengths equals to 1 between the star and the disk. The scattering is mainly responsible by the submicron dust in the disk. So the angular resolution of the direct imaging project is about 0.06 arcsecond, which translates into 8 AU in Polarized. And the inner working angle is about 20 AU at Polarized. This could be if you use a chronograph, then this is a chronograph size on super high power instrument. If you don't use a chronograph, then this is a little bit smaller. Would be the saturation radius of the image. But in any case, the point is the inner 15 to 20 AU is not directly accessible in the near-infrared image. So those are some of the recent results of these disk imaging. So the ABRIG object, you see the complex morphology. The SAO 26, 2064, 62, which you see the spiral. And this is a very, very recent publication they put together last month. So, in the first half of C's project, we concentrate on the so-called transitional, pre-transitional disk. So what are these objects? So here I'm showing you the typical SVD for one of these objects is the GMRE. So the black line, the black solid line here is SVD of GMRE, and there is a filter dash line here showing you the median Polarized SVD. To compare with the median SVD, which is presumably a full disk, for the dust, extend from the sublimation radius of about 0.1 AU all the way up to tens or hundreds of AU. So compared with such kind of disk, the transitional, pre-transitional disk has a near-infrared deficit and a dip around 10 microns. This has been interpolated as the depletion of the inner disk. And then its SED comes back again at 30, 40, or 50 microns. This bump here has been interpolated as there is a wall somewhere in the intermediate range, which is directly illuminated by the star to give you emission at this wavelength. So, yes, so in the literature, people have two names for this kind of object. Well, but as James was arguing earlier today, whether the name makes sense is another issue here. So, but in any case, so let's just go with this name. So for transitional disk, they mean the inner part of the disk is optically thin. For pre-transitional disk, they mean the inner part of the disk, there is an optically thick wall as a rim. For whether the pre-transitional disk is really pre-transitional is debatable. So this is SED. The other characteristic or signature for transitional object is their SMA interferometer image. So this is an image from China's paper. This is a some emitter, 880 micron. So as you can see, this is very clear. There is a ring here, and there is a hole or a cavity inside the ring. And if you translate this submillimeter, as submillimeter wavelength disk is typically optically thin, so the emission here is directly associated with your surface density. So if you translate this one into your surface density, you get something like that. So you have like a normal outer disk that increases with decreasing radius, and then suddenly your surface density is depleted by several order of magnitude. They have depleted radius. So these two pictures are actually consistent with each other. They are both telling you the inner part of the disk is depleted, like that. An outer disk and cavity inside. But so the recent CITA observation put a question mark here. I'll show you 3 examples. The first one is a published result. So SAO 2062 64 62. So this is a submillimeter image. The orange circle here is cavity size determined from radiative transfer fitting of the submillimeter signal. This is a seed image here. They're on the same scale, and circles are the same size here. So you actually see a loss of scatter light coming inside the circle. The black hole in the middle is, in this case, is a chronograph, so you don't have access to it. So you see loss of scatter light inside this submillimeter cavity, which tells you so the near infrared doesn't seem to have a cavity. Here is another object which has not been published. So this object, this is submillimeter image. The black circle here is a radius. This is a seed. This is seed image. This one is even in better contrast than the previous one. So this one, when you in the near infrared, when you cross the cavity edge, you see just no sign for the cavity whatsoever, and the scatter light intensity just increases inward until you hit the inward angle.
This is definitely not the capacity effect, because you're likely to come off the peak in the middle before you come off the peak in the near infrared. So
that's true. That's true.
Couldn't your dust to gas ratio just be the same, and you're just affecting your whole larger radii?
I guess, so the final point we're trying to drive here is, the submillimeter has a cavity, but submicron does not have a cavity. So another example here. So the previous two, they're pretty much face-on case. This one is a more inclined case. So the submillimeter image, it doesn't show you a circular ring, but in any case, showing just put a disk model which tells you this one also has a cavity with a size. If you put in a circle here, it's as a dash circle here. This is a seed image. Again, the same story. There's no sign for the cavity in your infrared image. So what's going on here?
What's the optical depth for the near infrared?
The optical depth.
What do you see in scatter light, as you said?
Yes.
So how much starlight are you seeing in those scatter light?
You mean like if you enumerate the total scatter light?
The tiny fraction.
Yes, I did try this number before. It's a small number. I think it's on the order of 1% or maybe a few percent. It's essentially the solid angle you intercept the starlight, which, well, it also depends on your, another thing here is, so this is polarized light, so it also depends on the dust property. Like, yes, like what's the polarization fraction? It's not going to vary when I'm magnitude, but like a factor of 2 is still possible. So what's going on here? To study that, so we run radiative transfer simulation we use a Monte Carlo code written by Ruobing. So here's our disk model. So we put a star here, and we have a two-component disk. We have a thin disk with dust size up to millimeter. And most of the mass is in the millimeter-sized dust. And the millimeter-sized grains are responsible for your sub-millimeter signal because the bigger dust have higher opacity than the small dust at this number of events, and also because they're more massive than that. And so this is a thin disk. There's also a thick disk filled with some micron dust. And the disk scattering surface is somewhere here. So the scattering is responsible by the submicron dust. So those are the 2 points to keep in mind. Sub-millimeter signal from big dust and scatter light signal from small dust. So if you run the simulation, it's going to give you images in any wavelengths. It'll give you a raw image. The raw image essentially has the infinite small spherical resolution, only limited by a photon noise and gray. Then we convolve this image by, for the near-infrared image, we convolve by a real observed super PSF. So then you get a convolved image. This is the image you can compare directly with what you see in observation. We actually, so I can go even into further detail. We actually also put like chronograph and visual map, this kind of thing there to make the final image really comparable to the observation. So before I take the result, so let's just review what are the direct observational facts. So we have 3 observations: the SCD, the near-infrared image, and sub-millimeter image. So the SCD, the 2 signatures here is you see a near-infrared deficit and a dip around 10 micron. Then the SCD comes back at 40 or 50 micron. This is SCD. Near-infrared, you see the scatter light increases radius all the way from the outer part to the inner angle, and you see no sign for no discontinuity at the cavity edge probed by the sub-millimeter image. And sub-millimeter image is the simplest one. It's just a bright ring and a cavity as the center. So radiative transfer simulation, what's going to do is going to just essentially translate a physical disk model into various observations. So if you put a physical disk model like this, so this is a traditional picture for a transitional disk. Everything is depleted within some radius. Then this is the image and SED you get. So in the SED, you do see a dip here, and near-infrared deficit because the inner part is missing. There's not too much material to give you infrared access here. And there's a wall receives starlight directly to produce this infrared quantity. Your near-infrared scatter light image, well, the same story. There's not much stuff here to give you scatter light, so you see a cavity. And your sub-millimeter image, the same story. If you convolve these 2, you will get those convolved image, which should be compared with observation. So the conclusion for this model is you get a correct, qualitatively correct, as you get a correct sub-millimeter, but not near-infrared. All right, so how to fix this? How to fix it? How do you view the cavity in near-infrared? The simplest way, as a naive person, I would just figure out the cavity here. I just figure out the cavity and I will just going to feel the near-infrared cavity. So what happened is, indeed, the near-infrared cavity is viewed because now we have a loss of dust here to the scatter light. It doesn't do much to the sub-millimeter because the micron size, sub-micron size dust, the opacity at sub-millimeter is very low. So even if you put more small dust here, it doesn't affect it that much. So we still fix the big dust structure at there. So yes, so if you convolve the 2, you get something like that. So those are you agree with observation. However, now the SED changes as well. So now you have material at the innermost disk. It will give you near-infrared access. And because this part of the disk is now substantially block direct stellar radiation to reach the disk at intermediate radius. So your infrared access at 40 or 50 micron decrease. So now your red SED here is actually some sort of like typical full disk SED. So this model gives you correct image but not SED. So the final solution we come is to design a surface density for smallest in this way. So it increased outward, increased inward in the outer disk. There's no discontinuity at the cavity edge and decreased inward and reach the same deflation factor as the innermost disk. So if you do this, the two images doesn't change much. So one thing to notice, the C is inner working angle. It's roughly here. So what happened inside of this part? You don't have direct constraint. But once you do this, you get SED as a green curve. So now your innermost disk is heavily depleted. So your near infrared access is suppressed. And also now your disk at intermediate radius range is directly exposed to the star much better than the red curve, which you actually can pick up a bump in the 40 or 50 micron. So this model here produced correct SED, correct near infrared, correct semi-mirror. Yeah.
Kind of a bump at 10 micron, so that still came from the hottest cluster.
You mean this?
Yeah.
Oh, this is a silicate fissure. This is this is essentially, so this fissure is produced by the bond between a silicate atom and an oxygen atom. So this is
It's a crystalline fissure, but it still came from the innermost regions.
To have a silicate fissure, the dust needs to be at 200 or 300 Kelvin or higher temperature. So 200 is 300 Kelvin. You don't, yes, it's relatively inner disk, but for a luminous photostar, you can still reach it maybe a few AU or so. So, just to review what we're doing here. We have three constraints from SE, and we have two components of dust. How do they correlate with each other? So the SE, the inner part has a deficit, also different on camera. I can tell you, the inner part of the disk has to be somewhat heavily depleted to suppress the infrared access. And the bond here tells you the material and intermediate radius can, to some extent, somehow indirectly illuminated by the star to give you infrared emission. The near infrared imaging, the inner 15 or 20 AU is blocked by the inner working angle, so you have no direct access for what's going on here. At the cavity edge, you see a smooth transition, which tells you there's no discontinuity or any kind of jump in the submicron dust structure here. Otherwise, it will appear in the near infrared. And on the other hand, the near infrared signal here doesn't tell you much about what's the structure in thick dust is. The sub-millimeter doesn't tell you much about the small dust. Then the inner part tells you that for the big dust, for the millimeter size dust, your inner disk is depleted. And if you actually read Sean this paper, you will find that in most of the time you can actually only put an upper limit for the depletion factor here. So the amount of small dust is below some limit. And the ring here tells you there is a relatively sharp feature at the cavity edge. So this is the model we put together. So a somewhat smooth, continuous, small dust, submicron dust, this structure, and a millimeter size dust with a huge inner hole in the center. So after we get this is also like somewhat unexpected. It's when C's targeted this transitional disk, we were thinking, okay, you're going to see cavity in near-infrared image to confirm previous result. But now we did. We put together this model. And now we're starting to think how to explain this physically. So Zhaohuan and I put together a paper, and there's others who put together a paper recently as well. So we come to the idea of dust filtration. So dust filtration was initially proposed by Cooper, Melman, and Rice a few years ago. So the basic idea is very simple. If you have a pressure peak in the disk, which can be caused by whatever reason, like if you have a gap opened by a planet, then the edge of the gap will serve as a pressure peak. Then a pressure gradient points away from the peak. Your gas is subject to the pressure gradient. So the inner part of the disk, you have supercapillary rotation. The outer part of the disk, you have subcapillary rotation. The dust will tend to go in a capillary velocity, but will be dragged by the gas. The net effect is in the inner part of the dust will go, well, in the inner part and outer part of the dust will try to go towards where the pressure hits. So the net effect is the dust is trapped by the pressure peak here, especially when your entire disk, the material is moving inward as part of the viscous process. But on the other hand, so this dust filtration mechanism only works best if the dust is big, because your small dust tends to well couple with the gas, so we just go with the gas. So this is a simulation of them. So yeah, so this is simulation done using Fargo, and so here for the gas, there's a planet. Open a gap here. The planet doesn't need to be very massive. This is a very shallow gap here. Then this is a density map for a 1 millimeter size dust. The dust filtration works here to trap the dust at the cavity edge, at the gap edge, and no dust can pass the edge. So you have this very deep diffusal of 1 millimeter dust. So here is small dust. It's not too small, but so 30 microns. You see the density deficit here is much shallower than for the big dust, because the smaller dust tends to be better coupled with the gas. So this model, as we put together, we were thinking maybe it's one way to explain the observation. However, that's not the end of the story. So very recently, the CITA observation actually indeed picked up a few objects. Well, yeah, actually only a couple, in which the cavity is indeed revealed in the near-infrared image. So this is showing you one example here. So this object is, so it's inclined to us, but still you see a very clear rim and a depleted inner region where not much clear light.
You will have to tell us which one it is.
Unfortunately not, but this is a paper Hashimoto, John Hashimoto and I are putting together. We're both together on everything a few weeks ago. So yes, and we also so the observational paper is close to submit. We followed up a radiative transfer volume paper, basically to pin down the parameters for the dust and pin down the parameter for the cavity and the disk. So essentially, qualitatively we know there's a cavity in a small dust. So what we did is we use a model to produce SED and image, and we fit both to the observation to pin down those numbers. So this is model image here, and this is the observed image, and this is SED fitting together. So I'll just flash it back and forth so you see the model fitting here. So eventually the number we get is you need about 3-order mapping depletion for small dust in this case. So this is actually
You're allowed to tell us whether it's
yes, so this object is not
not
there's no measurement for its accretion rate, but this object is classified as a weak line Polarized product. So the H alpha with its own two-dimensional line. Yes, so the last part of my talk, I'll just talk about some implication from the observation. So take-home message is, are we actually looking at two causes of transitional disk? Both of them have cavity in the big dust, millimeter-sized dust, but only one of them, the cavity also is present in the small dust component. In the other, the small dust is actually smooth and free. So if this is real, then naturally you want to ask why you're seeing two causes of transitional object. When we were thinking, this is purely just some theoretical speculation. So, there are many ways, as James was also talking about earlier this morning, many ways to argue how to form transitional objects, such as planet or multiple planets, green growth, MRI, just twin or binary. I won't talk about them, but I will just mention one thing which I think doesn't draw enough attention in a few recently, which is binary. So there are only a few objects which their cavity has been confirmed essentially in every wavelength, from near infrared, UV optical to millimeter to molecular line emission. And a particular group of them is the known binary system. So maybe one of the famous is a GG top. So this is GG top near infrared image. This is GG top millimeter image. So you see two dots here, and then it's the double star. The cavity opening process due to binary is very effective, as Paolo here did at work 20 years ago to study this thing. So we were thinking, would it be possible if the cavity, in a case where a cavity exists in both dust components, maybe you were saying a binary system. Another possible explanation is, or we're just looking at objects at different stages. So they all start with a full disk. Then somehow the big dust gets depleted first, leaving a small dust disk here. Then as time goes on, the small dust subsequently is depleted. Then you have the cavity both dust components. So one of the ways to do this, again, go back to this filtration model. If you have a pressure peak here, you trap the big dust. So your inner part quickly is depleted from big dust, but your small dust can go through inner disk to give you scalar light. But then later on, the small dust in the inner disk gradually grows into big dust. Then your small dust is depleted as well. So the last thing I will talk about is just mention some future observations which can improve our picture view. So in the sub-millimeter to millimeter, obviously everyone is talking about ALMA. ALMA has a higher sensitivity and a better angular resolution than the current instrument. It's about 2 and 1 order of magnitude better. So this is image showing the effect of ALMA theoretically. So those are two disk models. This one has a complete depleted inner region, and this one has a little bit of residual semi-luminous signal, which could be due to small dust or a small amount of big dust inside the cavity. So if you combine them with the current SMA ability, this is what you get. So they look essentially the same. The inner signal is essentially washed out. Very hard to pick up. So if you combine them by ALMA, you see the little bit of residual signal here can be or may be reviewed by ALMA. This is so if ALMA can pin down the amount of opacity inside the cavity, that will be a very useful information. So in the near infrared, there may be 30-meter telescope, but we don't know whether they're going to happen or not. The one thing for sure will happen is the 10-meter telescopes, they're building the next generation AO system and chronograph. For example, Subaru has a next generation adopted objects, which should be working in a few months or so. So this essentially the new instrument will give you a better point square function. So this is and also a smaller working envelope. So this is in fact showing you this is an image showing you the effect. So this is a disk model, which the smallest component has a small discontinuity as a cavity edge. So you see a small discontinuity in the raw inconvolved image. So the two panels are the same. If you convolve them, this is with the current Subaru PSF. This is with future, the next generation AO PSF. You see the contrast in this image is better. That is to say, you can pin down the discontinuity at the cavity edge much better with the next generation AO. And the third thing you can do is obviously you can try to get more objects for each category. So C's project will run for another 3 years, and Alma, full Alma will be online later next year as well. So to summarize the observational part, so the missing cavity, the near-infrared cavity was found missing in C's observation for actually a fairly large number of objects. So we propose a new model to explain this, which is the biggest component has a cavity, but the smallest component is relatively smooth. While density could decrease inward to give you a cavity depletion at the innermost part, and which may be explained by dust filtration plus dust growth model. And also recently, it's also found near-infrared cavity in some objects. So the question is, are we seeing two classes of objects? And if it's true, then what is the reason? So thank you very much for your attention. Questions? Oh, yeah, so I'll be around today and tomorrow. So office 14, 13. So anyone who is interested, please come to talk. Hey, John.
So you have the really high resolution to get the planet reports, right? But that was to get the details, right? So if you wanted to do global simulations,
yes, that's.
I mean, are you doing sort of good enough that you just reduce your resolution, or is it really going to depend on whether the planet's doing it or out?
That's really sensitively depend on the problem you're studying and to what extent you can tolerate the effect of the environmental simulation. So, so our simulation we focus on density. We're only running a simulation for 20 to 30 orbits. If you study gap opening, you're going to run a simulation for 500, 1,000 orbits. Unlikely you can afford such a high resolution. Actually, it's about 100, so they're running simulation these days with thousands of orbits. So,
sharing boxes. Those are sharing boxes.
Right now they're running, for 2D case, they're also running global simulation. So Athena can also do global simulation. So, this is a question very hard to answer. If you ask me, I would say, if you go with lower resolution and you lower other parameters, you're guaranteed to have inaccurate result. It's just to what extent it's going to affect it. I understand it's physically not very possible to run, but if you force yourself to go with low resolution, you're guaranteed to face this problem.
Well, Andrew McFadden, did you see Andrew McFadden was here for the talk? He has this code that has adaptive, so it's pseudo-Lagrangian. I think he was saying, I didn't quite understand all the details, but he was saying he was actually reproducing the guy's result much lower resolution.
Oh, I see. He's running a global simulation, right?
Yeah, but
yes.
I think the key point was that it was a Lagrangian mesh. But I don't know. I mean, this is more a complicated question. But
right. So we do receive emails. The two guys are from NYU, right? Yes. So they're running global simulation. So I think reasonably we produce the result. But if you actually check out the paper, again, we go back to the primary requirement. So it didn't provide actually at least some of the detailed comparison I don't know whether they didn't make this measurement or they made what they found the result is not very clear.
But to try and understand this new gap that is growing up. It's because it's nonlinear and non-local. So it's not like the old criminal couple.
Right, the old
where you have to get your hill state has to become orderly or scale. So that's you need your viscosity to be sufficiently low.
That's true.
That
That's
each
true.
shock.
That's true.
So the gap is much wider.
That's true. The stars is well, one of the very differences in the nonlinear shock case, you essentially open two gaps simultaneously initially. Then they may merge eventually, but which is different from previously people were talking viscous criteria, thermal criteria. But those are all for relatively large planets. You stick a planet into the disk, like it can control immediately evacuate the part of the disk close to it. So it's essentially two different ways of opening a gap.
How much viscosity do you need?
So if you ask me the number, I would say to see this, you need at least maybe your numerical alpha needs to be smaller than 10 to the -4, 10 to the -5. And of course, if you're running simulation with previous resolution, like 16 scale height per inch, and your numerical viscosity already exceeded this, so you're never going to see this two gap open. Yeah.
Make a short comment about the direct flashback of this spectacular picture by Nito at all. Spectacular image of Athena or whatever. I was going to comment that doesn't look like it does in the tradition. Yeah. So you really see dynamical interaction between the first and something else. And then interaction inside the gap, the outside of the gap, as a large scale phenomenon.
Yes, well.
Soft filtering, the pressure is maximum, local pressure maximum can generate all these features.
Sure, the dust filtration plus dust growth model is just, it's just our speculation, which is maybe possible. Even it's true, it may only work for a group of this kind of object. So in this particular case, the point quadratic model try to drive this spiral density here. So we try to use this to determine the shape of the wave. Well, the shape of the wave you can determine the scale height of this. This is very hard to constrain from other ways.
Well, this says, yeah, I agree. You can determine this parameter, but also I'm just saying that doesn't really can you use pressure filtration to explain these features as well? But that's probably too long a question. Just curious.
Yeah, I mean, the image looks to me is, the point they put in the paper is they say they're planets inside density. But this image looks to me, it could just be there's some dynamic, even instability happens there. So the spiral is just a natural way of this response to any kind of turbulence or like perturbation. Let's put it this way. So this image looks to me is just telling you that disk is not, it's not quiet. There is some perturbation in the disk, so the disk responds by showing you a spiral. It may or may not be fine.
Yeah, well, this will be an interesting system.
That's true, that's true.
Great, it's